goes from the positive peak to the negative peak forever. So this is marginally stable. Okay. Okay, so how do we know if a transfer function is any one of these systems? Well, we need the real part of every pole. We need the real part of every pole be less than 0. Okay. The real part of an unstable system would be greater than 0. Okay. And the marginally stable, the real part of P will be equal to 0. P is a pole. We talked about what poles were. Okay. Another way of saying the same thing, all right, go ahead and get a quick shot of this because I'm changing pages. Remember our pole 0 diagram? All right. We have 2 poles in this diagram, okay? And here's the right-hand plane of the S-plane. And here's the left-hand plane. Okay. We want our poles to be on the left-hand plane, okay? For a stable system. So for a stable system, all poles on the left-hand plane. Conversely, even if we just have one pole on the right-hand plane, the system's unstable. If just one pole is on the right-hand side, the system's unstable. And therefore we cannot build it. If, however, we have poles on the y-axis, then we have a marginally stable system. Any questions about that? These are just definitions that you must learn and understand.
Could you move your pen so I could take a step, please?
In practice, we want marginally stable systems when we want to create an oscillator. An oscillator is the thing that are in signal generators in the lab. That's how you generate a sine wave. To generate a sine wave, we need to create a marginally stable system. So most of the time we want stable systems, but once in a while we want a marginally stable system. I don't know of any situation in the real world you want a unstable system, because they almost always wreak havoc. Now we're ready to answer the question somebody asked me last class, even though we were studying something else. All right. Okay, final exam. Final exam is from last year. Okay. This is now question 3-2. Question 3-1 was determine all the poles and zeros. So we had G of S equals 20 S minus 3 S plus 10 over S squared plus 2S plus 5. Okay. And we found out the poles are S equals -1 plus J2 and S equals -1 minus J2. Okay. So, question 3-2. Question 3-2. Is this transfer function stable, unstable, or marginally stable? Give a reason for your answer. Well, which is it?
Will be unstable
Why is it unstable?
because all the points are on the left hand side.
As well as the
So
right.
that makes it unstable?
Stable if it on the left.
Could I?
Somebody has a question?
Oh, I wanted to give it a try. I believe it's unstable because one is in the left hand pole and one is in the right hand pole, and because of that, it's unstable.
I didn't say anything about left hand pole and right hand pole. Mr. Johnson, it amazes me how you hear things I don't say.
You said if any one of them
Plane.
are on the right hand pole, then it's unstable.
Clearly, you don't understand what a plane is. I said plane, not pole.
Oh, it's the they are on the left hand plane, so it's stable.
Absolutely. So S equals -1 plus J2. That's right here. There's -1. There's J2. So that's one pole. That's one pole. And then the other pole, this only has 2 poles. This has a quadratic. And so the other one is here at -1, -J2. So both of these poles on the left-hand plane. This is the left-hand plane. So the system is stable. Stable. Any questions about that?
I see my mistake. Thank you.
So, Dr. Cartwright,
Yes.
is it safe to say when alpha is a negative, it is stable?
Well, actually, that's what I said.
All right.
That's what I said. That's what I said. See, the real part of this pole is what? -1, isn't it? Isn't that the real part?
Yes, sir.
And the real part of this pole is what? -1?
Yes, sir.
Okay. So the real part is is less than 0. It's negative. So this is one of the reasons why we do pole zero diagram. You can look at the pole zero diagram and tell whether or not the transfer function is stable, marginally stable, etc. All right, that's all I'm going to do. Yeah. Young man, were you not paying attention to anything I said today? Where on this diagram would these poles be if that was a positive one instead of a negative one? So why are you asking me this question? They'll be here and it'll be here, wouldn't it? And what's the criterion for stability? Were you not paying attention when they said when the system is stable? I gave you three things. I gave you when the system stable.
Dr.
Wait a minute, no, somebody, I'm trying to answer that guy's question. Whoever that was. Young man, ask your question. When is the system stable? When all the poles on the left-hand plane, when all the poles on the left-hand plane, okay? This is on the left-hand plane. This is on the left-hand plane. Are these two on the left-hand plane? Where are they? All right, what happens when they're on the right-hand plane? Young man, what happens? Unstable.
What if you have a combination, Dr. Godray?
A combination of what?
Like when you have poles on the left and the right hand side, if that's possible.
See, again, I refer you to figure 2. If there's only one pole on the right-hand plane, it is unstable. Let me repeat, all the poles have to be on the left-hand plane to be stable. So if it's not stable, it must be unstable or marginally stable. I don't know why. I think I have an English problem in this class. The system here. What's the stability status?
That's marginally stable.
The root of the poles? What are the poles?
No, that's negative J2 and J2. So that's marginally stable.
These are the poles. And where are they located? J2 and negative J2. They're located on the y-axis. So this is what? A marginal stable. What about now? Is this a stable system or what?
That's unstable.
Yes, unstable. Why? Because this pole here is S equals 1. Where's S equals 1? Right here. Right-hand plane. Unstable system. This is unstable. That's what I said. If there is one pole on the right-hand plane, then the system is unstable. I mean, what time do you want me to say it? By the way, you're going to need to know this for 420 in the next semester in automatic control theory. All right, that's all I'm doing on stability. I have to move on. How is the step function related to the impulse response? You folks do not study.
The derivative of a step function is the impulse function, impulse response.
Okay. So u of t, the step function, is the integral of the impulse. Oh, I'm sorry, I shouldn't put response there. I should be impulse function. So u of t, step function, okay, is the integral of the impulse function. I gave you this earlier. But of course, most of you don't study. Right. Now, similarly, the step response is the integral of the impulse response. Okay. And I think we call the step response h of t. Okay. And the impulse response, I think we call g of t. So we can write h of t is 0 to t of g of t dt. Okay. For example,
I can see that for 1 second, please. All right, I got it. Nice.
All right, how am I going to do this?
Well, well, looking at that, I know that's 1 over S plus alpha. Yeah, that's the formula for f of S. That's T minus 4.
I have no idea what you said. You just said. What you just said makes no sense at all.
Um, all right, you see the 3 over S plus 3?
Yeah, what about it?
In the table, that would be T minus 4, or 1 over S plus alpha.
He say don't use the blast, man.
All right.
Oh, okay. I should have been clearer. Don't use Laplace to find the step response, but you can use Laplace to find the impulse response. Mr. Johnson, what were you saying?
I was confused. I know what to do now. I can find the impulse response.
Wait a minute, this is G of S, sorry. This book uses G of S for the transfer function. How do you find the impulse response? Because we want to use the equation I just gave you. We want to use h of t equals 0 to t of g of t dt. We want to use that. I just gave it to you. I want to apply it. So if g of s is a transfer function, what's g of t?
I know by definition, G of T is the inverse Laplace of G of S.
That is true.
Yeah.
What else is g of t called? What is g of t called? Folks, life would be so much simpler if y'all just learn your definitions when I give them to you.
The impulse response.
Impulse response, thank you very much. Okay? Impulse response. Okay? Let me say it again. Impulse response is inverse Laplace of transfer function. This should be said in your brain. So G of t is equal to how much?
That would be 3e 3t.
All right. So now what's the step response? The step response would be 0 to t, 3, e minus 3t dt, which is, we can bring the 3 out, 0 to t, e to the minus 3t dt, which is 3, e to the minus 3t, and what else do we have to do? What else do we have to do to integrate e to the minus 3t?
Evaluated at 0 and t.
No, before that. Well, good luck to you all on the final exam. This is stuff you should have known before the midterm.
And you dividing by -3.
Thank you very much. And for those of you who don't know why, I invite you to go back and check your notes. All right, so this would be the step response. Okay, now let's do it. Let's redo the same problem. But let's use Laplace transforms this time. So what's step response? What do we mean by step response? Oh, Lord. I think it's time to retire. I don't know if students expect to know things if they don't friggin' study.
That would be like the input step function equals to step response, something like that. It was showing us.
Yes, I showed you. That's the key word right there. That's the key phrase right there. I did show you. And did you learn it? No. Why not? Because you don't think you have to learn anything. Not you personally. The whole class thinks that they don't have to learn this stuff.
Isolate the output of a step voltage.
That's the output when the input's a step. The step response is the output when the input's a step.
That's what I said, or the guy, right?
That's not quite what you said.
Oh, that's what I meant.
It is not what you mean that counts. I don't grade what you mean. I grade what you write.
Okay, I say the step response is the output of the step signal voltage. That's what I say.
But that doesn't make any sense to what you just said. Can't you hear the difference when you
when input voltage is a step signal, the step response is the output.
Thank you very much. That makes sense.
Uh,
And what's the impulse response?
The impulse response is the output when the input is the input.
Yes. And what's the sinusoidal response?
output when the input is a sine wave.
Yes. See how simple that is? So we have, here's what the question is asking. We have x of t, we have y of t on the output, and this is a transfer function. Well, the transfer function right now, what is here? The impulse response is here. We talked about this. And this translates to what? This translates to x of s, g of s, s. So the input is a step, u of t. The output is by definition h of t. Or here, this is h of s. The step response in the Laplace domain. And how is h of s related? How is h of s related to g of s and x of s? How is the output related to the input?
Well, G of S would be the output over the input.
Therefore, how is the output related to the other two?
Is the word indirect relationship?
Yo, man, you're making this a lot harder than it is. You just told me. Listen to what you just told me. You just told me that G of S equals Y of S divided by X of S. That's what you just told me.
Yes, sir.
So how is Y of S related? Solve this equation for Y of S.
Y of S would be G of S times X of S.
So how is that? Why is that difficult? Y of S, the output, is the transfer function times X of S. Okay. What's Y of T equal to? What's Y of T equal to?
That's the impulse response multiplied by x of t.
Absolutely not. Absolutely not. I made a big production about that not being true.
You mean the convoluted?
Thank you very much, Mr. Johnson. Convoluted. G of t convoluted with x of t, and I showed you what convolution meant. And I told you we don't need to know how to do convolution, but we need to know that convolution is a separate mathematical operation than multiplication. I made this big deal about it because I know it's natural to think because this is true, that is multiplication is true, but it's not. Multiplication in the Laplace domain is not multiplication in the time domain. All right. So what's X of S?
That would be the inverse of Laplace of G of S.
Don't talk, fool.
I thought you said X of T. Sorry. Could you repeat it again?
I asked what's X of T.
Oh, I got it wrong.
What is X of T? Oh man, you clearly don't know Laplace transforms. How are you going to take the inverse Laplace of a function in the time domain? You can't take the inverse Laplace of any time function. That makes absolutely no sense. Folks, I think you all have forgotten what we're trying to do here. Somebody tell me, what are we trying to do?
Trying to find the step response.
And if we're trying to find a step response, what is the input? If we're trying to find a step response, what is the input?
The input is a step.
See it right here? See it right there? Right on the page.
Actually, yeah.
Right on the page. And yet I hear garbage like the bottom one. So what is X of S then?
With X of X, G of S times Y of X.
X of T is a step function. So what is X of S?
Will that just be the impulse?
No. You tell me X of S is delta of T? Does that make sense to you? A function of S domain is equal to a function of time domain?
I was talking about the X of T.
We just said X of T is U of T, so why are you talking about a delta function? If X of T is U of T, what is X of S?
In the Laplace domain, that's 1 over S.
It is one of S. Because Laplace of U of T is 1 of S. So this is 1 of S. That's 1 of S. So now what's the output? And the output is going to be what? Step response. Y of S equals what? G of S, the transfer function. What is that? 3 over S plus 3 times 1 of S. The input Laplace. So how are we going to find Y of T? So how are we going to find Y of T?
Could we do inverse Laplace? Find YT?
Yes, and how are you going to do that?
Well, we could cross multiply everything, get the result.
What do you cross multiply? What are you cross multiplying, young man? What are you cross multiplying?
I would do the S and the 1.
What does that mean?
3S over S plus 3.
Does that make algebraic sense to you?
Not much. No, sir.
How are we going to find y of t? Yes, y of t. Yes, y of t is the inverse Laplace of y of s. But how are we going to do that?
You just solve for y of s and find the inverse Laplace of that.
Yeah, man. How are you going to solve for y of s? I don't know what you mean by what solve for y of s. Y of s is 3 of s plus 3 times 1 of s. How are you going to solve for y of s?
I didn't mean solve. We probably could use like partial fraction expansion though.
Oh, partial fraction expansion. Finally. What is this in partial fraction expansion?
3 over s squared plus 3.
Wow.
Which one you look?
Oh, Lord.
No, 3 over s squared plus 3s.
A over S plus 3 plus B over S, eh?
Thank you very much.
Oh,
Thank you very much.
You trying to be falling off, we were going that.
no, but I didn't see what part yours were, you know.
Oh, what's A equal to? What's A equal to?
Three. Or I mean, whatever that is on the numerator, S plus 3.
That would be 3 over S evaluated at negative 3.
Well, it's -1, isn't it? What's B equal to?
That'd be 0. That would be B equals 3 over 0 evaluated. Wait. Sorry.
No, yeah, you get a 3 over s plus 3.
Sorry.
Evaluate at s equals 0.
You want it.
Which is 1. So y of s is 1 over s minus 1 over s plus 3. Okay. So what's y of t then? What's y of t?
So y of t, you'll find me do it, but that'll be 1 minus, or you can put u of t.
Yeah, I can put that in there at the end.
E to the negative 3t.
And all of that can be multiplied by u of t. And you see what? That's the same answer we got before. See, it's the same answer we got before. Except that we did it 2 different ways. The first way is we didn't use any Laplace transforms at all, other than to get the impulse response. We used this equation here. That's what we used to get this answer. On page 7, we use Laplace transforms. Why? We use the fact that x of s is 1 over s, and we know g of s, and we know that y of s. We know that the output is the transfer function times the input, Laplace. And then we did inverse Laplace. So there were two different ways of doing that problem.
So, Dr. Godray,
Yes?
in a final exam,
Yes?
could we choose which way we're gonna do it, or you?
Maybe not. If I don't say do it this particular way, then you're free to choose to do it any way you want. If, however, I say do not use Laplace transforms like I did on last year's final exam, I mean do not use Laplace transforms. And then you have no recourse but to do it the first way. And if you go ahead and do it the second way, you get great big zero. Because I'm not testing. Excuse me?
So you get only 2 points to get the correct answer?
Absolutely not. If I tell you to do it one way and you go ahead and do it another way, then you have not answered the question I asked.
Dr. Godray,
Yes, go ahead.
you mind flipping through the pages so I can catch the snaps?
Yeah, yes, I do mind. Why were you not snipping when I had them on the screen?
I was just listening to you. I totally forget. I guess the last on pages 5, 6, and 7. I totally forget the
Young man, I am not going to put up the screenshots just for you because you didn't bother taking the screenshots.
Yeah.
I suggest you get it from Mr. Buchan. He's pretty good. He's pretty good at doing these things. All right. Now let's go the other way. Let's go the other way. What we just did was the step response was the integral. What we just did was the step response was the integral of the impulse response. Now let's do impulse response. Impulse function equals derivative step function. Now, similarly, impulse response is derivative of step response. Okay. Plus now, you just have to take my word for this. This is on page. Let me find the page. You just have to learn it. I could prove it to you, but I don't want to take the time. You can see it looks strange. This is equation 754. Plus step response at t equals 0. Step response at t equals 0 times delta of t times delta of t. So another way of doing that is g of t equals derivative of step response plus h of 0 plus delta of t. This is equation 754. Just learn it. Just learn it. This part of it should make sense because of this, because you should know that. This part here is a surprise to you, and it's a surprise to you because we didn't cover something we should have covered earlier. We didn't cover equation 753. Let's do an example. Let's do step response. Let's do it. Let's do H of t is e to the minus 2t. Okay. This is step response. Okay. So g of t would be the derivative of this plus h of 0 plus. H of 0 plus is e to the minus 2 0 delta of t. Okay. And clearly this is 1. So the impulse response is going to be minus 2 e to the minus 2t plus delta of t. That's the impulse response. Yeah. We could do it this way, or we could do it using Laplace transforms. But first, before okay. All right, let's do it using Laplace transform. So h of t is e to the minus 2t. Okay. So what's x of t? What's x of t?
X of t was the step.
So what's x of t? Mr. Johnson, how do we write a step?
U of t.
So why did it take you so long to answer me? So right now, what do we know? There's a system that has x of t equals u of t, and an output y of t equals h of t, which is step response, which is e to the minus 2t. And this system, of course, has a transfer function. Hence, it has the impulse response. So,
Other guy, why you cross out the
because you don't put this is a time domain. This is time domain. You don't mix time domain and S domain. So corresponding to this, this is what we have physically. This is what the problem is saying. The problem is saying this is a step response. So that automatically tells you the input is u of t. It automatically tells you that. And the output is step response. And that system is going to have an impulse response g of t. corresponding to this is the Laplace domain. G of S, okay? X of S equals how much? X of S equals how much?
1
1 over
over
S.
Ah. And the output, what's the output equal to? Y of S or H of S, same thing.
That
What's
would be
Y
T
of
of
S?
S.
Hmm?
T of S times X of S.
What is the output? If this is the output in the time domain, what is the output in the Laplace domain?
1 over S plus 2.
1 over S plus 2. Thank you very much. So what do we know? We know Y of S equals G of S times X of S. So we know 1 over S plus 2 equals G of S times 1 over S. So we know the transfer function. The transfer function is 1 over S plus 2 divided by 1 over S, which is S over S plus 2. So what's G of T?
G of T is the inverse Laplace of G of S.
Which is what? I find the inverse Laplace of that.
The inverse Laplace of G of T.
Excuse me?
You asking what the inverse Laplace is of G and G of T?
I'm not asking what's the inverse Laplace of G of T. I'm asking what is the inverse Laplace of S over S plus 2? Because G of T is the inverse Laplace of S divided by S plus 2. You can't take the inverse Laplace of G of T. That makes no mathematical sense,
Well,
as I explained earlier. But apparently,
I know I said wrong, but I mean inverse Laplace of S over S plus 2.
well, that ain't what you said. And if you don't say it right, that means you don't understand it properly. What is the inverse Laplace of S over S plus 2? How are we going to find that?
E to the 2, E to the 2T.
Well, that's wrong for two reasons.
Oh,
It
E
would
to the
be-
minus 2T.
That's still wrong.
That's in the numerator.
S is in the numerator. Thank you very much. See, you don't know because you don't study.
You gotta use partial fraction expansion to start.
No, you cannot use partial fraction expansions yet. You cannot use partial fraction expansion yet. Why not?
Because I know I remember now. We gotta divide S of T by S because the degree is the same or something like that.
No, you got to divide S by S plus 2.
And it's because the thing.
This is S divided. No, there ain't no Tingham. There ain't no Tingham in electrical engineering.
You know what I'm trying to say, man.
But that doesn't help you.
But I know you divide S by S plus 2.
You know, a very long time. I used to hire people. I used to be the service manager for an electronics firm. I used to hire people. When people start talking about, you know what I mean, I say, no, I don't know what you mean. You have to tell me what you mean. And if you can't tell me what you mean, I don't want to hire you.
I thought you only used to teach.
Yeah, but why did you think that?
I know. I mean, that's
You know why you think that? Because you judge a person by what they are today. But what they are today is not what they've always been. Necessarily. In my youth, I was an electronics technician. Then I became electronics engineer, and then I became service manager. And then I got into teaching.
What company did you got, right?
A company that's now out of business. A company, a home electronics firm called Dudley's. It was the biggest one in the Bahamas.
That's after you got your PhD?
No, that's after I got my bachelor's. I didn't get my
working in the field instead. Why you want to get a PhD instead of keep working in the field?
Well, that's because I'd rather teach than work in the field. Different strokes for different folks. As a matter of fact, when I came to COB, when I came to COB, I had a firm offer from a firm that would pay me 1.5 times what COB is going to pay me. And I turned down that other firm, which actually turned out to be a good idea because they went out of business 2 years later. But nonetheless, I wanted to teach. I always knew I wanted to teach. I was a guy in high school helping all the other kids. Not at the same time, no. Well, doing high school, yes. Doing high school, yes. I worked, and actually during high school, I worked. I went to school. I worked after school, and then I did a home study course in electronics. I taught myself electronics through a home study course. That was the forerunner of non-face-to-face education. Home study course programs. Anyway, let's get back to this. The numerator order is the same as the denominator order. We've been through all this. Okay. So this is not a strictly proper rational function. As Mr. Buchan mentioned, we have to divide, but he said the wrong thing. We have to divide s by s plus 2. So that's 1, s plus 2, and that'd be -2. So this here is inverse Laplace of 1 minus 2 of s plus 2. Okay.
I just have a question. I'll clarify something. What makes this improper? Why is this improper?
I just told you. I literally just told you. Excuse me?
Because s in the numerator.
No.
Because then
Same order.
Okay.
The highest power in the numerator is 1. The highest power in the denominator is 1. If that had been s squared divided by s squared, that would have been the same problem.
What if it's s squared divided by s? They just have to be different.
You still got it. The numerator is still higher than the denominator. You can't have that happening.
That'd be improper. Okay.
What's the inverse Laplace of this?
(2e) to the minus 2t.
Oh, that's delta. Delta first for the 1.
Oh,
Yes, thank you very much. delta of t minus 2, e to the minus 2t. See there? See there? Same answer. Yeah, you can multiply this by u of t. It's understood that all these functions begin. You can multiply this by u of t, that by u of t, yeah, and this by u of t. That's understood.
So if you forget your T, you get points off.
I don't think I'm that particular.
Really?
Right off the card, right, trying to get a picture of page 9.
Which one? 8 or 9?
9. I got it, thanks.
All right. There's one last thing I should tell you about Laplace transforms. If you integrate a function in the time domain, what do you do with the original Laplace? Not equals, goes to. This f of s is Laplace of that. So f of s is Laplace of f of t. But if you integrate f of t, you simply divide by s. Isn't that neat? Actually, we've been using this. And I didn't tell you. For example, okay, what's Laplace of delta of t? What's Laplace of delta of t?
That's 1.
1. When we integrate delta of t, we simply divide by s. And what is this? Isn't this u of t?
Yeah.
So you see that checks. This is what you want to memorize. Because we didn't get to actually solve it. I told you every circuit has a differential equation, and we didn't get to how we solve those differential equations. You can solve differential equations using Laplace transforms. Why? Integration in the time domain becomes division in the Laplace domain. Similarly, ddt of f of t, the root of f of t is again fs, right? F of s, but not divide by s, multiply by s. But we're not done yet. We have to subtract the initial value of the function in time domain. Okay.
And you're supposed to times it by delta t as well?
What are you talking about?
Or this might be a different equation.
What are you talking about? Oh, sorry, this goes to they're not equal. This is Laplace. Okay. If you have a function f of t, okay, Laplace of f of t is f of s. And then when you differentiate the time domain, you differentiate f of t in the time domain. What do you do? What do you do in the Laplace domain? You multiply by s, but you subtract the initial value of the function in the time domain. This is little f. Let's do f of t equals a sine omega t. Okay. So what's f of s? What's f of s? Wow.
That omega over s squared plus omega squared.
A. You don't see the A? A omega over s squared plus omega squared. Okay. So let's differentiate this now. Let's differentiate A sine omega t. All right. What does that become? That became A omega cosine omega t, doesn't it? All right. So what is the plus of this? What's the plus of A omega over cosine times cosine omega t? What's the plus of A omega cosine omega t?
A omega s over s squared plus omega squared.
All right. Now let's use this equation here. Let's use that equation there. So we know this is what the plot should be. There. So what do? We take the original f of s. And what does it say? We multiply by s. And then we subtract what? F of 0 plus. But f of 0 plus is A sine 0, which is 0. So we subtract 0. And don't you see that this is the same as that? So that proves this rule. Okay. Any questions about that?
I have a question.
Yeah, go ahead.
I see in the formula. All right, where did we multiply s by the Laplace?
I did that right here. Don't you see I put the s there? Sorry, that should be s of f of s.
All right, that's what I was looking at.
So this term right here, that's this. And then we discover that this term here for this problem is 0. So the derivative of sine, Laplace of the derivative of sine is the Laplace of the original function, okay, multiplied by s minus the initial value in the time domain. These are 2 rules you must learn. And by the way, this generalizes the second derivatives, but we won't go there today. All right. That's a lot of work.
Sorry, guys, you can put it back 1 second. Eh?
That's a lot of work.
All right.
Okay. So now you're able, let me look at the,
Sorry, guys, ready to ask a question, please?
that is a question. You want to ask another one?
Yes, sir.
Okay.
Okay. I have a question, right? Like when I going over my notes, and okay, instead of putting like Laplace inverse 4 over s squared plus 4, like you pull the 2 out and leave 2 in the numerator. Why do you do that? I don't have to do it that way, right?
How else are you gonna do it?
Just take the Laplace inverse of 4 over s squared plus 4.
And how are you gonna do that? What rule in the table tells you how to do that? Let me write down what you're saying. Give me a second.
You know, like, okay.
You're saying inverse Laplace of 4 over s squared plus 4. That's what you said, right?
Right. And I saying in the notes you would have break it down and you would add Laplace inverse. You would pull the two out. You would pull the two out.
I would have put inverse Laplace of 2 times 2
Right.
of S squared plus 4. Now, why did I do that?
Yeah, because the omega is 2 squared.
This is omega squared, and it's supposed to be omega. That's the entry in the table. The entry in table, this is not an entry in the table. There's no entry in the table that says omega squared over S squared plus omega squared. No entry in the table. Because the entry in the table equals this. That's the entry in the table. Okay? So in this particular case, omega is 2. So this numerator has become 2. And what do we have to do? If we make that numerator 2, what do we have to do? We have to multiply by 2, otherwise we change the problem.
Right. Okay, I got you. Thanks.
All right. Now, I'm going to introduce the next topic. We won't have time to get into it, but I'm going to introduce it. What's a periodic waveform? This would be our last, no, maybe not. Depends how well this goes on Wednesday. Folks, I suggest you learn everything we do today because you'll have to learn new material on Wednesday. So if you don't learn today what we did today, you're going to be in trouble. Did I ever tell this class I have a 4.0 average in my PhD? Did I ever tell you all that?
I'm not sure.
All right. In my master's and PhD, I have a 4.0 average. I can show you the transcript, so you'll know I'm not bullshitting.
What about your bachelor's?
What about what?
What about your bachelor's? You didn't get a 4.0.
No, in my bachelor's, I was just like you all. I'm serious. I was just like you all. Studied the night before the final exam.
So what caused you to change
So what happened then? I barely, you have to have a B average to get in grad school, right?
You have to have a D average?
B.
Okay.
You have to have a B average to get into grad school. I barely got into grad school. Not because I couldn't do the work. I just didn't want to do the work, just like you all. And then before I went off to do my master's and PhD, I got married. And getting married, I became more responsible. So after every class in my master's and PhD, I learned that material. And I was also a teacher then. I taught for 2 years. So that helped me. That helped me to know what to look for in a lesson. Every lesson has a theme. Anyway, I would study that lesson and know it as well as a teacher before the next class. And I guarantee you, if you did that with every one of your courses, you'll get an A in every one of your courses. But that requires you to take the time to study the material.
The teacher got to be able to teach first, though.
No, bullshit. I taught myself electronics.
What's the point of a lecture then?
Well, the lecture should guide you. A lecturer should be able to teach the material. Ain't no doubt about that. But if you have a bad teacher, that ain't no excuse. Especially in this day and age when you got 1,000 YouTubes on the same subject. When I was doing my PhD, there was no YouTube. You don't have all these sites, all these educational sites.
God, do you think like YouTube and stuff like that, and they can make like formal education the way formal education can become obsolete eventually? What do you think? Like classroom style education?
Well, for some people, yeah, but not all. Some people like to have a lecturer, but you
I mean, like
don't
from the
need a
government. I
lecturer.
mean, from a legal standpoint. I mean, like from how the government of making mandatory to go in the classroom stuff like that. I mean, like from that standpoint, like school. And I mean, like for the whole nation.
You talking about high school?
You're right. Yes, sir.
Well, I don't know. I don't spend much time thinking about high school. You can teach yourself anything. When I graduated with my PhD, there was no internet. There was no internet. I
You
had to
didn't
teach
have
me.
access to internet.
No, I mean, there was no internet. Internet came about in the early 90s. I graduated in 1990 with my PhD. I had to teach myself the internet. PSpice that we do in class, I had to teach myself PSpice. We did PSpice in grad school, but it was with DOS. I don't know if y'all know what DOS is. That was the time. That was the time before Windows, and you didn't draw circuits. You didn't draw a circuit. You made a list of the circuit. You made a list of the circuit, and that code told PSpice what the circuit looked like. You had to write code. Remind me next class to show you the code I'm talking about. You had to write. And so when Windows came on the scene, I had to teach myself Windows, and I had to teach myself PSpice with Windows. The most important thing you can do is learn how to learn. Because I guarantee you, 5 years after you graduate, something's going to come along you never seen in your life. And if you haven't learned how to learn, you're going to be left behind. All right. Let me get to. Yes, you have to keep learning. Where's
Other guy, right? Do you ever like work with the government, like in electrical engineering?
no, don't want to.
You know Mr. Bradley King?
Yes, I know him. Yeah. I don't know him well, but I know him. We've met, we've talked.
Right, yeah. He told me. I asked him if he knows you.
Oh, okay.
He told me work with you one time ago, many years back. I think that's why I asked you that.
He what?
He told me that he worked with you on something many years back. That's why I had asked you that.
Really?
Yes, sir.
I don't remember that.
Or to say he encountered you doing something on a particular something of the sort.
Oh, we may have had some contact, but I don't remember working with him. All right. I'm out of time. We'll pick this up on Wednesday. We got things to do on Wednesday. So come prepared to work on Wednesday. Any questions or final concern? Go ahead.
Oh, I was just.
Any questions? Jonathan, you have something to say?
No, sir. Sorry for that.
Okay. Anybody else? All right. See you all on Wednesday.